There are two PowerPoint files for chapter 5. The first PowerPoint file was covering section 5.1 to 5.4. And so this new set of PowerPoint is covering section 5.5 to 5.10. And so this video will start with section 5.5. So 5.5, the section is on the mole and the Avogadro number. So you're familiar with words that identify a certain number of things. Like, for example, maybe you were aware that 24 cans are called a case. Or if you're at school, you want 144 pencils, it's called a gross. And paper, 500 sheets of paper is called a ream. Or at home, you're familiar with 1 dozen, which means 12 eggs. Or a dozen of anything would mean 12 of that thing. And so in chemistry, we also have a word that defines a certain number of things. And we are counting units in moles in chemistry. M-O-L-E, 1 mole is this number of particles. So please look at the 6022, and then you have 20 zeros after that. So it's a very, very large number. And so it's impossible to write it down, you know, without making mistakes, and it's too cumbersome. So we use the scientific notation for that number. And the scientific notation is 6.022 times 10 to the 23rd particles. And so this number of particles corresponds to 1 mole. So when you say you have 1 mole of atoms, for example, you have 6.022 times 10 to the 23rd atoms. And so the reason why in chemistry we need a word like that that defines such a huge number of things, it's because atoms are so small, so small that a very large number of them is needed and used, you know, in a chemical reaction, for example. And so to help you see how big this number is actually, so when you're told to gather a dozen of donuts, so you take a donut and you can put 12 in a big box, and it's already a fairly big box. But now if you were asked to gather a mole of donuts, which means 6.022 times 10 to the 23rd donuts, it would be simply impossible, because a mole of donut would cover the Earth in a layer of donuts 8 kilometers deep. 8 kilometers deep are 5 miles, 5 miles of a thickness of donuts covering the whole planet Earth. So it's just impossible to gather so many donuts and, you know, to start with, to make them. And so this really shows you that if you start with a donut which is fairly big, it fills your hand, then it's impossible to gather a mole of things that are that big. But if you gather a mole of atoms, then it's more manageable. Like here, one mole of carbon atoms would fill a container that sits on the balance here on the right image. So that really shows you how atoms must be very, very small, so that when you take a mole of them, you know, it's a manageable size. You know, it would fill your hand again, but that would be 1 mole of carbon atoms. So that really shows you how atoms are small, and that's why we need so many of them to be able to, you know, do science and deal with them, with matter. And so a mole is a quantity that contains 6.022 times 10 to the 23rd items. And so those items in chemistry will be atoms or molecules or formula units or particles. And each time you will adapt the word that comes after 1 mole. 1 mole of what is equal to 6.022 times 10 to the 23rd of the same thing, right? So like, for example, 1 mole of carbon atoms is the number here of carbon atoms. If you're talking about molecules, molecules are still very, very small, right? And you still can gather a mole of molecules of CO2, for example, and it would be 6.022 times 10 to the 23rd molecules of CO2. So this number, 6.022 times 10 to the 23rd, is called the Avogadro number. Avogadro is the scientist who found out about this number by doing experiments with noble gases. And so by definition, 1 mole is equal to 6.022 times 10 to the 23rd particles, where particles can be either atoms or molecules or formula units, or sometimes you can call them particles. And so you see that this is an equality, right? By definition, we have this equality between 1 mole and the Avogadro number of particles. And so when you have an equality, if you can recall what you learned in chapter 1, you will remember that we can use that as a conversion factor. A conversion factor that in this case will relate the number of moles of a substance to the number of atoms or molecules. And so out of an equality, we can write two kinds of conversion factors depending on which part of the equality we put on top and which part we put on the bottom of the fraction. So it's either 1 mole on top and the Avogadro number of atoms on the bottom, or the Avogadro number of atoms on top and 1 mole on the bottom. Same thing if it was molecules, it doesn't matter. You have to adapt, particles to what your problem is about. So let's use the Avogadro number and the equality to a mole to convert moles of a substance to particles, or vice versa. So let's look at the guide here first. So the first step would be to state the given and needed quantities. And you should remember from chapter 1, that's, information you gather from the text. Then you want to write a plan to convert moles or particles to particles, or moles, depending on which one is given and which one you want. Then you will use the Avogadro's number to write your conversion factor, and then set up the problem to calculate the number of particles or moles, depending on what is given and what is wanted. So let's go through an example here that will show how we do this. And the problem is to convert 4.00 moles of iron to atoms of iron. So the given amount here is 4.00 moles of iron, and iron has a symbol Fe. What do we want? We want to know how many atoms of iron that corresponds to. So if we draw the plan or write a roadmap, it will look like this. You start with moles of iron, and you want to change them into atoms of iron. So the equality that relates moles to atoms, we know now that it's the mole definition that says that 1 mole of iron is equal to 6.022 times 10 to the 23rd atoms of iron. So using this equality, we can write two conversion factors, and we have to decide which one we will write here. If you look, because you start with moles of iron, so you will want to cancel moles. And so you will want moles in the denominator so that you cancel the starting unit. So the problem when you write it completely looks like this. So you always start with the given amount. And here the given was 4.00 moles of iron times, and remember how the given amount is in the numerator. You multiply by the conversion factor that has the mole on the bottom, such that you can cancel moles of iron. And then the number of, the Avogadro number of atoms of iron is on top. And that's the desired unit, which will be left over when you have cancelled the mole units. In the calculator, you do 4 times 6.022 times 10 to the 23rd, and you obtain this number. So, of course, your calculator will display that in the scientific mode, because there's no way it can do it otherwise. And remember how to type scientific notation in your calculator. In the calculator that I recommend, you will need to do the second key, second function key, and then the x-1 key that has the little, the capital EE written above. So then you need to type the second function of the x-1 key, and the second function of that key is the EE key, and that gives you the capital E. That stands for times 10 to the power, and then you only need to write the exponent, right? So the 23, for example, here. And by using this EE function, you tell your calculator that the 6.022 times 10 to the 23rd is one number, and it will keep that together and not, you know, separate it into two entities. We need to pay attention to sig figs as always, and here we keep 3 sig figs because we have 4.00. That's 2 significant zeros there because we see the decimal point. So you will need to keep 3 sig figs. Let's practice now by calculating a number of molecules of carbon dioxide that is present in 1.75 moles of carbon dioxide. So the picture here is representing dry ice. Dry ice is a solid carbon dioxide. And what's particular with dry ice is that when you take it out at room temperature, it makes white vapors. You know, white vapors come out of the piece of dry ice, and you will see the piece shrink fairly quickly. And so that those white vapors are carbon dioxide as a gas. And what's particular about those vapors is that they will move downward. They are heavy. It's because carbon dioxide is more dense than air. So the vapors will fall down to the floor. And you will see your piece of dry ice shrink very quickly. And so this shows you how dry ice, you know, solid carbon dioxide, becomes gaseous carbon dioxide without going through liquid. So anyway, back to the problem here. How many molecules do we have in 1.75 moles of CO2? So the given amount here is 1.75 moles of CO2. The question is asking for a number of moles of, molecules of CO2. So we have moles and we want molecules. So we know that we will need to use the definition of the mole with the Avogadro number. And the particles here will be called molecules because it's molecules of CO2. And next, if we write the roadmap, we see that we start with moles of CO2 and we want molecules of CO2. And what will relate those two units is the Avogadro number and the definition of the mole. So the conversion factor, there are two kinds of conversion factor out of an equality. And here it's showing you the two conversion factors. Of course, when you are used to do this kind of calculations, you don't need to write all of this. You may go directly to writing the setup, the final calculation. So out of these two conversion factors, which one do you think we will use? Given that we start with moles of CO2, we want to cancel moles of CO2. So we will use the first one, the first conversion factor here to the left, because that will allow us to cancel moles of CO2 from the given amount with the denominator there. And molecules of CO2 will be on top, which is the desired unit. So if you set up your problem, your calculation, it will look like this: 1.75 moles of CO2, that's the given amount. Always start your calculations with your given amount. It's in the numerator, remember. You multiply by the conversion factor such that you can cancel the starting unit of moles of CO2 here. And you're left with molecules of CO2, which is what you want. In the calculator, you do 1.75 times 6.022, second function x minus 1, so that you get the E, the capital E, and then type 23, right? Remember how the E stands for times 10 to the power. So you don't need to write times 10 and the caret key. All of this is not necessary. The E stands for all of that. And again, it's a very large number of molecules, because that's what you should expect when you have, you know, a reasonable number of moles, like 1.75. You should get a very, very large number of particles, a number in the 10 to the 23rd, 24th, or 22, but something close to the Avogadro number. And here again, we keep 3 sig figs, because the given amount had 3 sig figs. And the Avogadro number is not limiting because it has 4 sig figs. The 1 mole on the bottom here is exact and is never going to be limiting. So we keep 3 sig figs, 1.05 times 10 to the 24th molecules of CO2. Make sure that when you are recording a number from your calculator, if your calculator is in scientific mode, it will show you the times 10 to the power. And you should report that, right? The answer is not just 1.05. You have to record that it's times 10 to the 24th. Otherwise, you completely change the value of your answer. And that would be completely wrong. So make sure you pay attention. If your calculator is in scientific display mode, then record the exponential part of your number. Let's practice some more with this problem. How many moles of sulfur are in 1.8 times 10 to the 24 atoms of sulfur? So the given here is a number of atoms of sulfur, 1.8 times 10 to the 24th atoms of sulfur. The question is asking for how many moles that is. So moles of sulfur. Again, between moles and atoms, you connect by using the Avogadro number or the definition of the mole. And here it's actually showing you the roadmap. The roadmap shows that we start with atoms of sulfur, and we will use the Avogadro number or the definition of the mole to find the moles of sulfur. So conversion factors can be of two kinds, depending on you know, if you, which part of the equality you put on top and which one will go on the bottom. And so out of 1 mole of sulfur equals 6.022 times 10 to the 23rd atoms, you can write 2 conversion factors, and they are shown here. So out of these two, the first one or the second one, which one do you think you will need in this particular calculation? So because you start with atoms of sulfur, you will want to use the conversion factor that cancels atoms of sulfur. And for this, atoms of sulfur have to be on the denominator of the conversion factor. So we will use the first one. And then when we write the full calculation, it looks like this. So it's 1.8 times 10 to the 24 atoms of sulfur. It's your given amount. You always start your calculations with the given amount in the numerator. Times the conversion factor such that you cancel the starting unit. And here the starting units are atoms. So you will put the Avogadro number of atoms on the bottom and 1 mole of sulfur on top. Atoms cancel, we're left with moles, which is what we want. In the calculator, it is, so you do 1.8 times 10 to the 24th divided by 6.022 times 10 to the 23rd. And here it is very important that you use the EE key of your scientific calculator, because if you don't, the calculator will take the 1.8 times 10 to the 24th divided by 6.022, and then it will move the times 10 to the 23rd to the numerator. And this will completely change the answer, because it will give you a number very, very large with a 10 to the maybe 45 or 46. You know, the exponent will be 10 to the 46 or 45, which is completely wrong here. Those 10 to the 24th over 10 to the 23rd, they will actually kind of cancel out, and you will get a reasonable number, because a number of mole should always be reasonable. It should not necessitate scientific notation. So here you see that it's equal to 3 when it's rounded to 2 sig figs, because we have 2 sig figs in 1.8 and 4 sig figs in the Avogadro number, and the 1 mole is an exact number. So we need to keep 2 sig figs in the end, and that will be 3.0 moles of sulfur. So to help you with the rounding here, the calculator answer was 2.989, etc. If you need to keep 2 sig figs, you keep the 2 and 0.9. But what comes after the 9 is a 8. So you need to round up. And 2.9 rounded up is 3.0. So that's why it's 3.0 moles here. Another problem. Here it's asking how many moles of water contain 2.60 10 to the 23rd molecules of water. So the given here is the number of molecules of water, 2.60 times 10 to the 23rd molecules of water. The question is asking for moles of water. And so again, we will use the definition of the mole and the Avogadro number to connect moles to molecules. And here you adapt the particles to molecules of water. And so out of this equality, we can write 2 conversion factors. And here the conversion factors is already shown. You will use the conversion factors such that the molecules of water are on the bottom and the mole is on top. And the reason is because the given number has units of molecules of water, and we will want to cancel the molecules of water. So we will keep the molecules of water on the bottom and have the moles on top. Sorry, the roadmap is showing now, and here it shows that we start with molecules of water that we want to convert to moles of water. So if we write the setup, it's 2.60 times 10 to the 23rd molecules of water. And remember how the given amount is always in the numerator. It's what you start your calculation with. And you multiply by the conversion factor. And the conversion factor is such that molecules of water are cancelled. The units are cancelled. And so we are left with moles of water at the end, and it's the desired unit. So here you do 2.60 10 to the 23rd divided by 6.022 times 10 to the 23rd. And your calculator answer is 0.43175, etc. So here, again, the 1 mole is an exact number. The Avogadro number has 4 sig figs, and the given amount has 3 sig figs, right? The 0 is significant here because we see the decimal point. So we will keep the least number of sig figs, which is 3 here. So keeping 3 sig figs, the calculator answer, in the calculator answer, we keep the 4, the 3, and the 1. What comes after the 1 is a 7, so we'll need to round the 1 up to a 2. And so it's 0.432 moles of water. And again, here it is very important that you use the scientific notation in your calculator. Or if you don't, at least put parentheses around the Avogadro number in this case. Any number that is in the denominator, it is important that the calculator understands it's one number and not, you know, a number multiplied by a power of 10. So if you have issues with how to use your calculator, please reach out to me, okay?